Have you ever wondered how your files are actually stored across multiple disks in a RAID system? Here we have a 1 megabyte image file, a RAID controller, and 3 physical disks: Disk A, Disk B, and Disk C. In this video, we'll follow this image step by step as it gets divided into blocks, stripes, and chunks, and then stored across the disks, with parity for protection. It all starts when an application, like Photoshop, saves your 1 megabyte image. This file is handed to the operating system, such as Windows or Linux. But the operating system doesn't store the file as one big piece. Instead, its file system prepares to break it down into smaller 4 kilobyte blocks. The operating system, through its file system, like NTFS or ext4, takes our 1 megabyte image and divides it into smaller units called file system blocks. Here, each block is 4 kilobytes. That means our 1 megabyte image becomes 256 small pieces, ready to be handled by the RAID controller. Next, the file system blocks are handed over to the RAID controller. This is the brain of RAID. The controller doesn't just dump data randomly across disks, it organizes. It groups many 4 kilobyte blocks together into larger units called stripes. Here, with a stripe size of 256 kilobytes, our 1 megabyte image is divided into exactly 4 stripes. In RAID 5 with 3 disks, each stripe is divided into chunks. 2 disks store data, while the third stores parity. If you want to know how parity is calculated, I will explain it later in this video. The key idea is that the parity rotates, so no single disk is always carrying the load. For example, in Stripe 1, Disk A and Disk B hold data, while Disk C stores parity. In Stripe 2, Disk A stores parity, and the data shifts to the other 2 disks. This rotation keeps performance balanced while still protecting against a single disk failure. Each stripe chunk is then written onto a single disk. With our settings, each chunk is about 128 kilobytes. But disks don't actually write in chunks. They write in much smaller physical units called sectors, usually 4 kilobytes each, so that one chunk becomes 32 sectors, stored sequentially on the disk platter or inside SSD cells. RAID 5 relies on a simple but powerful math function called XOR. When we XOR 2 bits together, the result is 0 if they're the same, and 1 if they're different. This property makes XOR perfect for generating parity that can later be used to recover missing data. In a RAID 5 stripe, 2 disks hold data, while the third stores parity. Let's take Disk A with the value 170, and Disk B with the value 204. The controller computes parity by using XOR. The result is 102, which is written on Disk C as parity. Now imagine Disk B fails. Can we recover it? Yes. By XORing the data on Disk A with the parity on Disk C, the controller rebuilds Disk B. 170 XOR 102 equals 204. So Disk B is restored, and the system continues to operate without data loss. So let's recap what we've learned. A file is first divided into blocks by the operating system, then grouped into stripes by the RAID controller. These stripes are split into chunks across disks, with parity calculated using XOR. In RAID 5, your data is protected. Even if one disk fails, the missing information can be rebuilt instantly from the parity. This is the balance of performance, storage efficiency, and redundancy that makes RAID 5 so widely used. Thanks for watching, and I hope this gave you a clear picture of how RAID works behind the scenes.